So if we look back, we've seen how to take a motion diagram, which is a freeze frame photograph, for example, Diagon Lane's the bowling alley problem, or the walk in the park problem. We were able to map out motion by looking at an object's position at various points in time that are equally spaced in time and see some nice patterns. And then we're able to take those patterns and graph them, and we found out that if we graph position versus time, we'd get a motion graph, which we were able to interpret. So let's use those interpretations now, and let's take a generic graph. I just made up this graph right here. And we're going to learn how to take these graphs, whether it's a position versus time, and later on we'll do a velocity versus time, we'll switch to an acceleration versus time. And can we actually tell by looking at the graph what the object is doing? And couldn't we go backwards and figure out what the motion diagram looks like from it? So for example, here we have a position versus time graph. Well, right away, this graph is a little bit meaningless because we don't have any labels, so let's do that first. So we're going to assume for this case, we're doing one-dimensional motion here. So either we're going to take something that's moving on an x-axis, left and right, or forward and backward, or we'll have a y-axis moving up and down. All right. For this case, as you can see up above here, but we're going to use a horizontal motion vehicle, or somebody in a car or a bicycle, or somebody running back and forth on a track. And we will use MKS units. So let's go ahead and label our axes then. Well, x is the variable we use for a horizontal motion. We have a horizontal, for math class, your horizontal axis is the x-axis. And that's, for us in physics, represents your position in a horizontal dimension. For MKS units, positions are going to be meters. And then our other axis, we're going to be breaking this out in time. All right. And the first thing we should do on this is let's just see if we can take this motion. Let's turn it into a motion diagram real quick. And as you recall, a motion diagram is what if we were to look at this at equal spacing in time, like every second or every 2 seconds or every half a second, and actually plot out where the object is at every one of those points in time and look at that pattern. So when you're making a motion diagram from a motion graph, it's sometimes easier for the x motion in particular, because we have a horizontal motion, to actually turn your paper sideways or rotate it 90 degrees so you have your horizontal axis shown. And if you don't mind, I'm just going to draw a mirror of that axis right up here. Here's my plus x direction. I'm going to match up my numbers. Here's 0, 1. And in this case, our forward direction I'm going to define as towards the positive x side of the axis. And if I'm moving towards the negative side, I'm just going to call that reverse. Or you could call it to the right or to the left if you like. And remember what a motion diagram is. The key about a motion diagram is you've got to pick a time interval, an equal time interval, to show your motion of your object. And the time interval I'm going to use is every half of a second for my delta t. Our graph right now is set up for every second. So if you don't mind, I'm going to come through and just show the half-second intervals here real quick. So here are half-second intervals, just so we can track them a little bit easier. And really all we're doing to make a motion diagram from a motion graph is we have to plot the motion back and forth on the number line that it's moving back and forth on. All right? And so we can actually plot these points. These are the points we have to plot. I'm just going to mark every time we cross over one of our half-second or full-second intervals. And all we're going to do is plot those points on our motion diagram, which is our freeze frame diagram, taking pictures every half a second to see where the object is every half a second. All right, so I've drawn in several dots here. At time 0, our object is right here, and I'm going to label this at 0 seconds. So I'm going to make a dot for I'll put a filled-in dot for my object, and then I'll label the time right above it. At time 1/2 second, which is this guy, we're still at the same spot. All right, so we're also here at a half a second. At time 1, we're still at the same spot. So I'm just sitting in the same spot for 0, 1/2 second, and 1 second. Half a second later, now we're at time 1.5. We've moved over to -1. So my object has moved to the right at time equals 1.5 seconds. All right. My time, once again, at time 2, another half second later, I've moved over another unit to the right. And now you can see I've moved over 1 unit at a time every half a second. And by the way, that tells us that our velocity equals, we moved over, every half a second, we moved over +1 meter. So what's our average velocity for that case? What's 1 divided by half? It's actually 2 meters per second, which is the slope of that line segment right there. So that's +1 meter, and our delta t is 1/2 second. So that's another way to read these graphs. All right, so we were at, what time were we? Did just leave off at? This is at t equals 2 seconds. So at 2.5 seconds, we're actually sort of backing up here. So I'm backing up, and it looks like I'm backing up for every half a second. I'm backing up a quarter of a meter, another quarter of a meter, another quarter of a meter, another quarter of a meter. So if you don't mind, I'm going to switch over to a different color so you can distinguish it moving backward here. I'm going to move it down below the line. So we started out right here, and we're going to move back a quarter, back a quarter, back a quarter, and back a quarter. So here we are matching up at 4 seconds. This is at 3 seconds, this middle one, and this is at 2 seconds, which is the same dot as that. All right. So now we're moving backward. Here we're moving forward. Now we're moving backward. All right. And technically these are all on the same line, but if I drew them exactly on the same x-axis, all the dots would overlap each other, and I wouldn't be able to see them very well. So just remember that all these dots should be literally going back and forth along the x-axis. All right. Now all of a sudden we're going to move forward again. So I'm going to switch colors to move forward again here. So now, so I was sitting right here. Half a second later, I'm at about, I don't know, negative 3/4 of a meter. So now I'm moving back over to the right here. So maybe I'm right here right now at 4.5 seconds. And then at 5 seconds, I'm actually back at 0. All right. So I went from here to here to here. There's 5 seconds. And then at 5.5 seconds, I've actually moved a nice big jump this time. I've moved over to here at 5.5 seconds. And then at 6 seconds, I'm way up at 3. And you can see at 6 seconds what's happening. So I've jumped that far, then that far, then that far, then that far, in equal time increments. And what does that mean? That means we're accelerating. So that's how you can go from a position versus time graph back in to get your motion diagram. All right, so let's take a look at this homework worksheet. You'll notice there's the same position versus time graph in the upper block. The first thing I'm going to do is I'm going to label my axes like I had before. I'm going to use time in seconds, and I'm going to use my position in meters. All right, and we're going to use X again. We're going to assume this is horizontal motion. And the first thing we're going to do is describe the motion of the object for each segment. Remember, there's a certain set of motion words which are very easy to use to describe motion. If you keep it simple with the words, then you can easily describe motion very accurately. Just stay away from the word acceleration. That's my warning. All right. So if you look back on your 12 little position versus time graph worksheet, we went through a series of exercises to come up with a general set of rules for interpreting these motion graphs. So segment A is a horizontal line. What's a horizontal line mean? Well, in this horizontal line, we are at the same position at every point in time from time 0 to time 1, which means we're stuck at position -2. We're stopped at x equals -2 for 1 second. That's what that's doing. So for segment A, you are stopped. And for these general descriptions, you can decide if you'd like. Don't use. I'm just looking for the motion words. If you want to add some numbers to it as well, that's fine. So you could just say object for segment A, the object is stopped. For segment B, this has a positive slope, and that slope is that we calculate it. For segment B, we have a positive slope. And what does slope mean on these graphs? I mean, we're going to have to answer this for part D in any case, so I'm going to start right now on this. Well, let's figure out the slope for this segment. Well, slope equals rise over run And this is the work you need to show the first time you do any slope. After you do the first slope, the other ones you can just show a little bit of quick work, and I'll show you what I mean by that. Slope equals rise over run. Well, our rise variable is the x, is delta x. That's on our vertical axis. The run variable is on our horizontal axis. That's our t variable. It's delta x over delta t. And you might recognize that. That's our formula for average velocity. All right? Or you might recognize it by looking at the units. Well, the delta x units are in meters, and the delta t units are in seconds. Well, there's meters per second, and once again, those units show us it's a velocity. All right? That's how we know what the slope of a position versus time graph is. We're going to use that same process on this graph and on this graph. If we look at the slopes carefully, we will figure out what the slope on each one of these graphs can be interpreted as, just in the exact same way. So, remembering that slope means our velocity, we have a positive slope on this part segment B, so it means it has a positive velocity. In fact, if we plug in our numbers here, our slope in this case, and here's the short work I was talking about. We move up plus 2 meters, and we move to the right, our run is plus 1 second. And I can just plug that in. Plus 2 meters over plus 1 second equals 2 meters per second. That looks like velocity to me. So for part B, we have a slope. It's a constant slope, but slope means velocity, so that means it's a constant velocity. So a linear piece of your function means it's a constant velocity, or speed if you want to keep it in simple words we talked about before. So I'm going to call this a constant speed in the positive direction, which means forward direction. So the other you could write on this, you're moving at a constant forward speed, all right, for segment B. Segment C is very similar. Segment C, we're moving, it's a negative slope. That means we're moving at a constant speed in the backward direction. And that's all I need there. And if you want to put what the speed is, feel free to do so. Or better yet, call it velocity, because velocity includes that speed plus your direction. For part B, our velocity was plus 2 meters per second. The plus represents the forward part of it, and the 2 tells you how fast it's going, the magnitude. For segment C, if you look at do a little bit of math, our slope is what? Where our run is 2 seconds, and our rise is negative 1 meter, so we're at negative 1/2 meter per second. All right, there's the negative means we're moving backward. The 1/2 tells us how fast we're moving. So if we were to compare the speeds between parts B and C, part B, maybe we're saying we're moving quickly forward, and part C, maybe we're moving slowly backward. All right, and maybe this one we could call quickly forward. All right, so we've got a fast motion and a slow motion. Part D, what are we doing? In part D, if you could see my magical slope tool here, we don't have a constant slope on this, which means we don't have a constant velocity. Anytime you have a curve, you have a changing slope, which means you have a changing velocity, which means you have a changing speed. The question is, how is the speed changing? Well, this is a nice graph, and I'm going to represent my magical slope tool moving on here by showing a few spots where I'd hold it. I start at the bottom, and it looks like on this curve, it sort of flattens out at the bottom if I move from one point to the other. We're getting steeper and steeper and steeper. And of course, what I'm doing here is I'm actually lining up my magical slope tool so that it makes a tangent to the curve at several different points. And if you'll notice what's happening at these points, I start out with a 0 slope, 0 meters per second, and then I go up to a positive slope, a more positive, steeper slope, steeper and steeper, still positive, steeper and steeper, still positive. So what's that mean? Initially, we start from a stopped, I'll put this in quotes, you got to be careful about using the word stop, so you have to be there for a period of time to be stopped. But we start from a 0 velocity, and then we're moving forward, and we're getting faster and faster and faster. So I'm going to say moving forward, and we're going to say increasing your speed. And you can say moving faster and faster, that means the same thing. I would take that for a good answer. So use the graph to find the distance and displacement of the object. And maybe what I'll do is I'll do this in green, so you can differentiate it from the other work here. Well, how far, let's see, well, we need to know what the difference between distance and displacement is. Remember, distance is your odometer reading. If you move forward 10 feet, your odometer goes up by 10 feet. If you move backward 5 feet, your odometer goes forward another 5 feet. Odometers always move forward, and that's your distance. So that's your odometer reading. All right. Displacement, on the other hand, if you move forward 10 feet, then move backward 5 feet, then your displacement would be 10 minus 5 or plus 5 feet. And you'd use a sign in that because it is directional. It is a vector. So this is a vector, and negatives count against positives. And at the end, you always have a direction as well that goes along with your size. So, well, how far did the object travel? Well, let's go back to our motion diagram. Not this time I'll move a motion diagram along the side. Initially, we're just sitting right here, right? And then the object moves up this far, which is how far? 2 meters. And then the object actually turns around and comes back 1 more meter. And then the object turns around again and moves up to here, all right, which is 1, 2, 3, 4 more meters. Now, if we're talking about distance traveled, we add all these distances up. So I have 2 meters plus 1 meter plus 4 meters equals my distance, all right, which is going to be 7 meters. My displacement, on the other hand, I've got to take into account the negatives on here. So my displacement, which is delta x, I would actually take, I moved positive 2 meters, minus 1 meter, and then I move forward 4 meters. If you take that into account, we've got 4 plus 2 is 6 minus 1 is positive 5 meters. The positive means we end up moving forward. The positive means we move forward. And the 5 tells us our magnitude, how far we moved. Easier way to do this, though, is you take your x final minus your x initial. My final position is right up here, and that's at positive 3 meters. My initial position is right here. Here's x initial, and that equals negative 2 meters. And let's see what happens when we plug that into a formula. So I'm going to take 3 meters minus, my x initial was negative 2 meters, 3 minus meters. That's the fastest way to do it, folks, right there. Take your initial and final point and use it. For part D, find the slope for segments A, B, C. I already did that. We're all set. For the curved segment, the slope is changing. So what I suggested you do is let's find the slope at 3 different times. All right? Remember, the physical meaning of slope means your velocity. So here's the first time they ask you to do it at 4 seconds, and we're going to use our magical slope tool, which we already drew in here. Our slope at 4 seconds is what? It's 0 meters per second. We have a 0 slope at 4 seconds. Now, I have to sort of freehand these in, but you should definitely use a ruler. If you don't use a ruler, you'd be losing points on this. But at this point right here, at 5 seconds, I'm going to lay my ruler up here and come up with, hopefully, I'll see if I can freehand it in here. That's not a bad tangent. My tangent is about right there. And then I can take the slope of this tangent. You'll notice the slope of this tangent right here is, the rise is plus 2 meters over plus 1 second. And, all right, so the slope at time equals 5 seconds is positive 2 meters per second. So sure enough, we set up above in part D, we start at no speed, and we're increasing our speed. 1 second later, we're moving 2 meters per second. What's the slope at time equals 4 seconds? Or where are we at? 6 seconds down. So let's work that out. So let's find the slope at time equals 6 seconds. Once again, we've got to draw a tangent at this top point up here. All right, so we're looking for that point up there. Now, the problem with drawing a tangent up there, you're missing the top part of your curve, so it's hard to balance your ruler on an end point. But let's just pretend we can see this curve continuing to curve further and further upward. And so we can sort of estimate maybe if you draw your ruler on here, something like that. All right, so here's my new slope. I went from here, and it looks like I'm connecting down in here someplace.
So it looks like I've gone plus 4 meters in plus 1 seconds. This is my rise over my run. And so it looks like my final point up here is very steep. It's plus 4 meters per second. Now your numbers, because you're going to put your ruler on and draw a tangent a little bit different than I did, you might get 4.5 meters per second or 3.5 meters per second or something like that. Perfectly fine. This is an estimate you're doing, and your estimate's will be a little bit different than mine, but as long as you're close, you get full credit. All right, so we did part E. So we can see, as we had said before in our description up above, as time progresses, we're going faster and faster and faster, and that's what happened. Now it says to find the slope from time equals 0 to time equals 6. All right? It also asks you to find the slope from 4 to 6 seconds as a separate problem. I'll let you do the second problem yourself. But the first problem, from time equals 0 to time equals 6. Well, here we are. I'll do this in red. Here we are at time equals 0. Here we are at time equals 6. So I'm going to just draw a line from there to there. That's called the secant line. And we're going to find the slope of the secant. As you recall, the slope of your secant gives you what? It gives you an average velocity. All right? So we're going to find the slope of the secant is m equals our change in position over our change in time. Well, that's our definition of average velocity. Our change in position, we actually already did this. We did this in part C, the last part. We found that our delta x was positive 5 meters. That was our displacement. Our change in time is, well, we're going from 0 seconds to 6 seconds. We've gone forward 6 seconds. So our slope here is positive 5.6 meters per second, and that's actually our average velocity. So our average velocity, which is our slope over that time interval for the entire trip of this vehicle, is positive 5.6 meters per second. So right from your graph, if you wanted to figure out the average velocity, you draw a point at the beginning of your graph, you draw a point at the end, take your ruler, connect the two, find the slope. Slope is rise over run, delta x over delta t. You just found the average velocity. So if you were to do the same thing for 4 to 6 seconds, that would be right here on my curve, from the beginning of the curve to the end of the curve, and that gives me my average velocity for that curved section. Now, here's the next part, part 2. We're going to use the information we just worked out above, and we're going to use that to create a graph of our velocity versus time function. And if you don't mind, I'll clean up our work from the last section, and we'll refer back to it. So I'm just going to summarize the work we did from before. For segment A, we said the slope was, what did we say the slope was here? It was 0 meters per second for the entire segment. For the slope here, for part B, our slope was what? Meters per second. For part C, we had a constant slope again. It was linear. Our slope equals, what did we say on this one? Negative 1/2 meter per second. And then for part D, we actually had a few slopes. We had a slope here at time equals 4, and our slope here was 0 meters per second. We're not moving at all for that instant in time, at least. At this point, we found our slope was positive 2 meters per second. And at this point, we estimated our slope to be, that's at 6 seconds, our slope to be positive 4 meters per second. All right? Let's just read this first question. We're going to label our axes first. This is a velocity versus time graph. So this is velocity in the x direction in meters per second, our units. And we're going to use time in seconds. And we always use the same time scales on these graphs, so we can line things up and see what matches up with what. So let's just do part B now. The slope at any point on the position versus time graph represents the velocity of the object at that point in time. All right? So we're going to use this concept that these slopes I wrote in red up here are velocities. So slope equals velocity. Well, if we want to plot a velocity versus time graph then, well, all of our data we're going to take from above and use it down below here and just plot it. So, for example, for the first second of time, what speed is the object going? Well, it's going 0, 0, 0. The slope is 0 the whole time here, so we're moving 0 meters per second the whole time. So for this first second, I'm moving at 0 meters per second, 0 meters per second. I'm just sitting right here, not moving at all. I'm at 0 meters per second. For this next time interval, from time 1 to time 2, I have a constant velocity of positive 2 meters per second. Well, here's positive 2 meters per second, and I'm moving at 2 meters per second the whole time. All right, so I just plotted that data right down there. For part C, for that 2-second time interval, I'm at the same velocity the whole time, at negative 1/2 meter per second. Well, here's negative 1/2 meter per second. And so I'm going to plot, starting right here, I'm at negative 1/2 meter per second the whole time on this section up here, section C. So I'm going to keep myself at negative 1/2 meter per second down below here. All right, I'll connect all those. Because those are straight lines, which means they have a constant slope. What happens if you have a changing slope? Well, we picked out 3 points on here, so let's pick out each one of these points individually, plot them individually. So my first point at 4 seconds, we found this to be, when we looked at the tangent, to be at 0 meters per second. The second point at time equals 5 seconds, we estimated that to be at 2 meters per second. The third point we plotted up above was at positive 4 meters per second. So that one's going to be, I'm running into my other graph, but that's fine. I bumped these together so we could run over this as before. And that one is at 4 meters per second. All right? So my question is, what's happening in between? Well, what do you think? Well, I'm going to guess that since these three lined up in a line, 1, 2, 3, I'm going to guess that probably all the points in between are lining up. So as we move along our graph here, our object, the slope is getting steeper, 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 which means we're moving up this graph, and our velocity is increasing, increasing, increasing. So that's our velocity versus time graph. Did I need to make any assumptions to do this? No, I didn't. You'll see why I'm asking this later. Find the average velocity on this graph. Well, the average velocity should be this over here. We'll talk about that, a way to do this later in class together, and we'll see that it comes out to be 5, 6 meters per second using a different method. But the best way to get our average velocity is to use our position versus time graph to get average velocity. Now it says to repeat what we did in part 1. So in other words, find the slopes of this graph on the velocity versus time. So we want to find slopes. And then we're going to calculate the slope, see what the meaning of the slope is, and then figure out what happens. And I'll give you a hint. It has something to do with down here.